This video, we analyze an MCAT passage on quantum numbers and solve each question step by step. To get the most out of this practice, try the passage on your own before watching the solutions. Let's get started. Recently, scientists have been able to gain detailed insight into the valence electron properties of the iron atom at the center of hemoglobin. Using a technique known as the FELH X-ray absorption spectroscopy or FELH XAS. In the FELH XAS, the spectrometer uses X-ray photons to excite a 2p electron to an unoccupied 3D orbital. This excitation creates a core hole in the 2p level, leaving the iron atom in an electronically unstable excited state. To relax this instability, an electron from a higher energy level, such as the 3s orbital, can drop down to fill the 2p core hole, emitting a photon in the process. When the 3s electron fills the 2p vacancy, the resulting emission provides scientists with information about the electronic environment of nearby orbitals, particularly the 3D electrons. By analyzing both the absorption and emission processes involving the 2p and the 3s levels, scientists can determine the number of unoccupied 3D states, the spin configuration of the 3D electron, and the nature of the bonding interaction between the iron 3D orbitals and surrounding ligands in the active site of hemoglobin. As a result, FELH-XAS has enabled a deeper understanding of the electronic structure of iron in hemoglobin and its ability to bind oxygen. Question number 1. If the iron atom is replaced with a zinc atom, how does this affect the FELH-XAS results? Question number 2. Which of the following graphs best corresponds to the electronic transition of the electron in iron as it moves to the 3D orbital? Question number 3. How many unpaired electrons are present in the electron configuration of neutral iron? Question number 4. What happens to the angular momentum quantum number L as the electron transitions to relieve the instability caused by the absorption of the X-ray photon? So here's the passage analysis. On this slide, you can see the type of notes that I would take on a real MCAT exam. However, we're going to go through each paragraph and explain what is important and what to look for. The first paragraph reads, recently, scientists have been able to gain detailed insight into the valence electron properties of the iron atom at the center of hemoglobin using the technique known as FELH-XAS. The first paragraph serves as an introduction and it explains that the scientists used this technique to better understand the properties of the iron atom at the center of the hemoglobin. The second paragraph reads, in FELH-XAS, the spectrometer uses X-ray photons to excite a 2p electron to an unoccupied 3D orbital. This excitation creates a core hole in the 2p level, leaving the iron atom in an electronically unstable excited state. To relax this instability, an electron from a higher energy level, such as the 3s orbital, can drop down to fill the 2p core hole, emitting a photon in the process. The second paragraph describes the process used in the FELH-XAS. There's no need to memorize all the details. However, it is important to recognize familiar topics such as electrons in the 2p, 3D, and the 3s subshells. We should note where these details appear and anticipate one or two questions related to these subshells. The next two paragraphs provide information about the usefulness of the absorption and emission processes and explain how these processes help scientists gain insight into the electronic structure of iron. The main idea of the passage is the FeLHXAS provides detailed insight into the electronic structure of iron in hemoglobin by analyzing electron excitation and relaxation processes. Let's move on to the questions now. Here, the question number one reads: if the iron atom is replaced with a zinc atom, how does this affect the results? Option A says zinc and iron both have 2p electrons, so the spectroscopy technique can provide detailed information about the electronic structure of both. Answer choice B says zinc lacks the appropriate electronic compositions in the required subshell for this type of spectroscopy. Answer choice C says this type of spectroscopy produces much stronger and sharper signals for zinc than for iron. And answer choice D says the spectroscopic results are unchanged for both atoms since they both contain the appropriate subshells. Let's see why the answer choice is B. This type of spectroscopy works by exciting a 2p electron into partially filled 3D orbitals. Iron has partially filled 3D states, which makes this technique very informative for studying its electronic structure. Zinc, however, has a completely filled 3D 10 subshell because there are no available empty 3D orbitals for the electron to transition into. This type of spectroscopy does not provide useful information for zinc. Therefore, replacing iron with zinc disrupts this spectroscopic procedure and it makes choice B the correct answer. A good method for this question is to reword it and explain the question in your own words before looking at the answer choices. The main information in the passage that helps you to select the correct answer is in the second paragraph. This paragraph specifically states that this type of spectroscopic technique, the spectrometer uses the X-ray photons to excite a 2p electron to an unoccupied 3D orbital. By comparing the electron configurations of zinc and iron, we can see that the zinc atom does not have an empty 3D orbital, which makes option or answer choice B the correct answer. Let's move on to question number 2. So question number 2 says, which of the following graphs best corresponds to the electronic transition of the electron in iron as it moves to the 3D orbital? So to understand this question, we need to understand what happens to an electron's energy when it transitions from the 2p subshell to the 3D subshell in iron. First, recall that the 2p orbitals belong to the principal quantum number is equal to 2 energy level, while the 3D orbitals belong to the principal quantum number 3 energy level. In general, orbitals with a higher principal quantum number have higher energy. This means that when an electron transitions from 2p to 3d, it must absorb energy because it is moving from a lower energy orbital to a higher energy orbital. So therefore, the correct graph must show the electron initially at a lower energy level, which is the 2p energy level, and then the electron ending at a higher energy level, which is the 3D after the transition. Options A, B, and D are not correct because any graph that shows no change in energy, a drop in energy, or a final energy level lower than the starting point is not correct. So the correct answer is option C because the graph shows an increase in the energy from before to after the transition, representing the electron absorbing energy as it moves from the 2p orbital to the 3d orbital. So, for this type of question, it may be difficult to determine the correct answer just by reading the question stem alone. For some questions on the MCAT, it is often helpful to read the question stem first and then quickly scan the answer choices. This allows you to identify the one key detail the question is testing and focus your attention accordingly to that specific detail. In this case, look at the axes of the graph. The axes reveal that the question is asking about the energy difference between the two electronic states before and after transition. Once you recognize this, the problem becomes much simpler. You only need to determine which orbital has higher energy, the 2p or the 3d orbital. By narrowing your focus on this single concept, you can eliminate the incorrect option quickly and choose the correct answer without wasting unnecessary time. With that strategy in mind, let's move on to question number 3. Question number 3 reads: how many unpaired electrons are present in the electronic configuration of neutral iron? So, to determine the number of unpaired electrons in neutral iron, we first need to write its correct ground state electron configuration. Iron has an atomic number of 26, so its electron configuration is Ar 4s2 3d6. Next, we focus on the subshells that contain unpaired electrons. The 4s subshell contains 2 electrons, and because there's only one s orbital, those 2 electrons are paired. This means the 4s subshell contributes 0 unpaired electrons. Now let's look at the 3d subshells. A 3d subshell contains 5 orbitals. According to Hund's rule, electrons will occupy each orbital one at a time before they start to pair up. When we place 6 electrons into the 5d orbital, the first 5 electrons each occupy a different orbital, giving 5 unpaired electrons. The sixth electron must pair with one of the first 5 electrons. And as a result, one orbital becomes paired and 4 orbitals remain unpaired. Therefore, the 3d subshell contains 4 unpaired electrons, and since the 4s subshell has none, the total number of unpaired electrons in neutral iron is 4. This question was a simple discrete MCAT type of question, and it did not even require the use of the passage. Let's move on to question number 4. So, question number 4 read: what happens to the angular momentum quantum number L as the electron transitions to relieve the instability caused by the absorption of the X-ray photon? So, it is stated in the second paragraph of the passage that after the X-ray photon is absorbed, a 2p electron is excited to the 3d orbital, creating a core hole. To relieve this instability, an electron from the 3s orbital drops down to the 2p orbital. The angular momentum quantum number depends on the type of orbital. The s orbital have L is equal to 0, the p orbitals have L is equal to 1. Since the electron moves from a 3s orbital to a 2p orbital, L changes from 0 to 1, which means it increases. Therefore, the correct answer is A. This wraps up the video. For more concept review and practice, check out the other videos in this playlist or the links in the description below. Thank you for watching and best of luck to you on your MCAT journey.